This section explains why a disorder of distributed interaction demands a different kind of measurement. A disorder that lives in distributed interaction resists any instrument that probes one place at a time. That is the chapter's pivot. Task-based functional MRI biases you twice over. You pick the stimulus, then you pick the stimulus, then you pick the seed region, so you only ever confirm the network you already suspected. Venkataraman's move is to drop both. Resting state synchrony, no external stimulus, no hand-chosen edge, and a Bayesian generative model that asks a different question. Not whether this pairwise correlation is different, but which latent subnetwork best explains every edge at once. The altered circuit is inferred, not presupposed. Here is the transferable primitive. When the phenomenon is holistic, replace hypothesis-driven measurement with generative inference over the whole. Univariate tests ask where you told them to look. This framework tells you where. This section explains why autism research shifts its unit of explanation from the connection to the region. Autism resists the connection. First playbook. You measure every pairwise correlation, hunt group differences after the fact, and the findings never replicate. The reason is simple. A connection carries no biological address you can return to. Venkataraman's inversion is the generative move. Posit that a handful of latent region labels, the disease foci, generate the entire altered connectivity pattern, then infer them from noisy resting state functional, MRI. The unit of explanation shifts from edge to node, and that relocation is the whole chapter. A region has anatomy, so a focus can be verified by direct stimulation and can seed the next study. An edge or a scalar graph metric cannot. Unbiased means the model chooses the foci, not a prior seed. The disorder is the smallest cause producing the data. This section reframes working memory through network science. Working memory is a graph reconfiguring rather than a set of regions lighting up. The older activation-based map asks which nodes fire. Network science asks a different question: how the whole community structure repartitions. The chapter's single finding is that load drives one transition. As the task hardens, the brain slides from a modular organization, seen at rest or under light demand, toward a more integrated one. The degree of that slide tracks performance. Modularity is therefore a tunable order parameter, not a fixed anatomy. The same nodes remain, rewired. The honest note is this: the lens added no new regions. Its yield is the dynamics of segregation versus integration, the axis that activation maps cannot see. This section explains how Connectomics reads cognition as a shift in the brain's network structure. Cognition shows itself in how the brain's community structure reconfigures. At rest, the connectome sits modular, dense within each cluster, sparse between clusters. Under working memory load, it slides toward integration, growing more cross-module links, and the steepness of that slide tracks task accuracy. The signal lives in the reconfiguration itself, not in which regions light up. Dagenbach picks working memory as the test case because it is the best charted construct, so whatever network science adds is legible against a known baseline. The surplus is exactly this segregation to integration transition. Task demand is the control parameter, setting where on the axis the brain rests. That is the chapter's job in the book. It is the proof that Connectomics reads cognition as dynamic topology rather than localized activation. This section explains why a region of the emotional brain has no single fixed job. A region's function is set by the coalition it joins at a given moment. Pessoa dissolves the phrenologist's premise that each region owns one job and belongs to one network. A node instead holds graded membership in every community at once. What it computes is whatever coalition it currently affiliates with. Two axes generate the picture. The first is overlap. Region R sits in Network 1 under one context and in Network 2 under another. The second is dynamics. Coalitions form and dissolve as tasks shift, so a network's own identity blurs across time. The generative move is to read the brain as a time-varying graph, a function P of the set of networks, N and time T, rather than a fixed parts list. From this follows the chapter's quiet surprise. Activation and coactivation dissociate. A region can rewire its influence over the network without firing any harder. This section explains why a brain region has no fixed function, only an affiliation. A region carries a membership vector across communities, its entry summing to 1, and that vector is re-indexed by context and by time. Pessoa's move is to replace the hard partition where each region belongs to exactly one network with soft, overlapping membership. Region R composes into Network 1 here, Network 2 there, and what it computes is whatever its momentary affiliation composes to. Emotion and motivation are the anchor because they recruit precisely such shifting, distributed assemblies rather than a dedicated seat. The primitive to carry is this. Whenever you meet a partition, ask whether the true object is a membership distribution and whether that distribution is static or a trajectory. This section explains why the individual functional connectome counts as unique and how that uniqueness is proven rather than asserted. Uniqueness is never asserted here. It is earned by retrieval. The chapter's move is to convert an unmeasurable claim that each brain's wiring is its own into an operation you can run and score. Take a subject's functional connectivity matrix from one day and see whether it correlates most strongly with the same subject's matrix from another day, whether than with anyone else's. When the within subject correlation beats every between, subject correlation identity is recovered. It is a nearest neighbor lookup, nothing more. The connectome becomes a biometric, and success rates near 99% are the proof. This is what the chapter is for in the book. It establishes that individual functional connectivity is stable and idiosyncratic enough to ground later prediction of behavior from brain organization. This section explains why a person's functional connectome behaves like a fingerprint. The correlations between brain regions stay stable enough across days, tasks, even years, that a single scan can be picked out of a crowd by nearest neighbor matching alone. The entire chapter turns on one move. A subject scan correlates with their own other scan more than with anyone else's, so identity is an invariant of the correlation structure, not of any single region's activity. This inverts the field's reflex. Neuroimaging averages people into groups, but here the individual is the signal, and the group average is what erases it. The identification rate is not the aim. It is the instrument. It measures how much of you lives in the wiring. This section explains why a neurodevelopmental disorder is a property of the whole brain graph rather than a single broken region. The move is to stop asking which region is broken and start asking how the whole graph is balanced. A neurodevelopmental disorder, ADHD, or autism is a disturbed topology, the standing tension between segregation, which is dense coupling within a subnetwork, and integration, which is traffic across subnetworks. This reframes the older reading of hyperconnectivity and hypoconnectivity, the connection by connection account of which links are stronger or weaker, without discarding it. The strength facts survive as a special case, recast into global summary measures that the connection level view could not compute. The generative primitive is that a disorder localizes to no node. It lives in the imbalance of a system-wide ratio. Once you hold that, every later disorder in the book, addiction, schizophrenia, Alzheimer's, becomes the same question asked of a different balance point. This section explains why a neurodevelopmental disorder is best read as a property of the whole brain graph rather than a single broken area. A neurodevelopmental disorder stops being a broken region the moment you draw the brain as a graph. The nodes are regions, the edges are correlated activity, and once you do this, the pathology lives in the topology, not in any single part. The chapter makes one move. It recasts ADHD and autism as disruptions of the balance between integration and segregation. How tightly subnetworks cohere internally versus how much they talk across. The older hyperconnectivity and hypoconnectivity story, where this link is too strong and that one too weak, survives as a special case. It is subsumed rather than opposed because topology simply carries strictly more information than edge weights alone. The primitive to keep is this. Symptoms are graph-level invariants, so measure the whole before blaming a piece. This section explains why decades of dopamine-centric pharmacology bought almost nothing. Best-case nicotine abstinence stays below 12%, and what reframe finally pays. The reframe that pays is this. Addiction is a miscalibrated control loop. Its pathology lives in how brain regions couple, rather than in any single region. 3 networks are in play: salience, executive control, and default mode. The insula switches which one holds the wheel. In the addicted brain, that switch sticks toward internal craving, with reward overpowering control. Once the disease sits in the coupling, the therapeutic target slides off the neurotransmitter, which is global, off-target, and useless, onto the edge itself. Focal stimulation of the left dorsolateral prefrontal cortex retunes one connection while leaving the rest alone. Localize the disorder in topology, and the intervention finally becomes addressable. This section reframes addiction, moving it from a single spot in the brain to a balance between brain networks. Addiction stops being a place and becomes a balance. The dopamine story, mesocortical limbic reward gone wrong, is anatomically rich yet clinically barren. Decades of interrogating that one node yielded no intervention. The chapter's move is to promote the locus to a topology. 3 large-scale networks and their coupling carry the disease. The salience network, seated in the insula, is the switch. It arbitrates between the default mode network, which carries internal craving, and the executive control network, which issues external command. In abstinence, the coupling between salience and default. The generative primitive is this. When a single cause account yields no lever, the pathology lives in the coupling between regions rather than in any single region, and functional connectivity is how you read it. This section traces how schizophrenia came to be understood as a disorder of connection between brain regions rather than damage within any one of them. A century before anyone could measure a correlation between 2 brain regions, Bleuler named the disorder for its mechanism. Schizophrenia, the splitting of the mind, is not a lesion in any region, but a dissolution of the integration between them. That is the chapter's thesis. Schizophrenia is a disconnectivity syndrome, a pathology of the edges, not the nodes. Kraepelin's epigraph seeds it, no single symptom is pathognomonic, so the disease must live in the pattern, the composition, never any one part. Friston and Frith, in their 1995 PET demonstration of frontotemporal disconnection, turned the metaphor into a measurement. The modern fMRI toolkit that follows only refines where and how the integration fails. This part explains why schizophrenia is best read as a disorder of the connections between brain regions rather than of any one region. Schizophrenia lives in the edges of the brain graph. Its scattered symptoms, hallucination, disorganized thought, blunted affect, refuse localization to any single region, so the chapter relocates the disease to the relations between regions. Bleuler's own coinage already carries the claim, schizophrenia, the splitting of the mind, a Goler's. Every fMRI method is a distinct projection of that one relational disorder. Seed correlation, independent components, graph metrics, dynamic network states. Their convergence is what makes it real. The default mode and thalamic hotspots, the simultaneous hypoconnectivity and hyperconnectivity, a connectome too rigid to shift between states. The generative move is this. Read a brain as a network, then let the illness be a property of the wiring. This part explains why the connectome, the brain's wiring diagram, is the right phenotype to study when you want to find genes. The connectome is a phenotype closer to the gene than behavior is, and that proximity is the method itself. Twin studies fix the premise. White matter architecture runs 55 to 85% heritable and functional connectivity somewhat less. So the wiring diagram becomes an endophenotype, an intermediate readout between genotype and cognition, where the causal chain is shorter and the variance lower. Genetic signal that behavior drowns survives here. Everything composes from this. Single gene disorders and chromosomal deletions serve as natural causal probes. Then common variants, each of vanishing effect, force the move to consortium-scale genome-wide association studies to recover power. Here is the contrast that fixes the structure. Behavior is the noisy distal phenotype, connectivity, the quiet proximal one, and you sample where the noise is least. This section explains how genes reach behavior through the brain's wiring and why inserting that wiring as a measurable middle layer organizes the whole chapter. Genes do not reach behavior directly. They shape the wiring, and the wiring shapes behavior. Insert the connectome as a measurable middle layer, an endophenotype, and diffuse genetic signal condenses into something a scan can read. That single move organizes the chapter. At one end sit rare mutations, where one gene visibly bends a tract, Huntington's Fragile X, the deletion syndromes. At the other end sit common variants, each nudging connectivity by under 1%, where causality dissolves into statistics and only tens of thousands of subjects can recover it. The pattern the whole chapter turns on is effect, size buying legibility, big effect and rare reads as causal, small effect and common reads as polygenic. The endophenotype is what makes either one visible at all. This section explains why brain connectivity has to be treated as a moving structure and how the right container turns that motion into a signal for Alzheimer's disease. Brain connectivity is not a fixed graph. The correlations between regions drift even at rest, so a single correlation taken over the whole scan averages away the very signal that separates a healthy brain from a diseased one. The generative move is to stop treating each sliding window snapshot as an independent matrix to cluster into guest states and instead stack them into a tensor whose third axis is time. Then let structure, rather than a chosen cluster count, carry the model. Sparsity, because real networks are sparse. Low rank, because regions move in modules and change smoothly. The thesis is that the right container plus the right invariance beats PCA and clustering sharply enough to read Alzheimer's off the connectome. This section explains why stacking brain connectivity over time turns a static measurement into a tensor whose extra axis carries the signal. Stack the same connectivity matrix at successive time windows and you have a third axis. The chapter's whole move is to stop treating that axis as noise to be averaged away. A single Pearson correlation over the full scan collapses time, discarding exactly the drift that carries the disease signal. Arrange the sliding window estimates into a spatial bitemporal tensor instead, and the same two priors do double duty. Sparsity and low-rank find modular structure across regions and smooth variation across time. The biomarker is then inter-subject variation in that joint object, not any fixed edge weight. Here is the primitive. When a measurement is assumed static, the discarded dimension is usually where the signal lives. Restore it as a tensor axis and regularize along it. This section explains why the chapter treats 3 ways of reading episodic memory off a brain scan as partners rather than rivals. There are 3 ways to read episodic memory off a functional MRI scan. The first is voxel, wise activation. The second is pairwise, or C-based connectivity. The third is whole, network graph metrics. These are conventionally narrated as a succession, where each generation supersedes the last. The chapter's move is to refuse that succession. Each of the 3 measures a structurally different object, a node, an edge, a graph. Because they answer non-substitutable questions, they compose rather than replace one another. Localizationism is not incomplete because it is wrong. It is simply incomplete. Segregated local processing and distributed integrative processing are both real and both are needed. So, the chapter functions as the book's methodological conscience. It is a plea to harmonize the univariate legacy with network neuroscience instead of letting the newest tool overwrite the signal the older one still carries. This section explains why episodic memory serves as the test case for a single structural claim. The method you use to read the brain fixes what the brain is allowed to be. 3 analyses form one axis. Univariate localization sees isolated activations. Bivariate connectivity sees pairs sharing information. Multivariate network analysis sees whole graph topology. Each statistic precludes the questions the next one answers. Localization decomposes cognition into region functions. Connectivity admits that regions integrate. Network analysis makes integration itself the object. The chapter's thesis is that this progression tracks a shift from segregation to integration and that memory needs both. Measurement grammar bounds the ontology you can recover, so the field should climb the axis without discarding its lower rungs.